Okay. Hopefully you all practice balancing equations. So is everybody feeling pretty good about those? And hopefully some of them, like I said, are more trying than others. They take a little while to adjust the coefficients and then may take a little time. Some are pretty quick, so it kind of matches up nicely if you follow the rules that we went over on Monday. Okay, today is a big day for you for chemistry this semester because this is one of the most important things. I know I'll probably call everything important, but this is one of the most important things you learn in Chem 111. Okay, so we build on it just like we've been kind of building up to this point. So from last week to today, to Monday, what we've been building up for is to be able to do reactions and the calculations that I'm about to show. Okay. All right, so now that we can balance equations, so everybody looks like they feel okay about those. Okay, how about converting from grams to moles? Everybody feel pretty good about that one step? And then if we do in the reverse, moles to grams. Okay, so hopefully everybody feels pretty good about that as well. Okay, so now we're going to take the grams to moles sequence and we're going to put it together with a balanced equation. Okay, it's not that it's hard, it just takes some practice and you have to really understand it. There are kind of cheat shortcuts to this method, but you don't understand what you're doing. So my job is to teach you, but also to teach you in a way that it makes sense, that you can understand it. So we're not going to use shortcuts where you just memorize because then next semester you're going to forget. Okay, so we're going to try to show you how to set up your conversions just like we've been doing pretty much all semester on and off. Okay, and we're going to work through it. Okay, one of the main things that you have to do is you have to read the problem and pay attention to what it's asking you for. Okay, so some students, word problems is, they just kind of scares them. Okay, you have to see what you're asked for and know where to start. Okay, so I'm going to help you today in knowing where to start, which is what I always say, is you start with what you know, right? So that's where you're going to start, so you can at least do that much. Okay, to this point, when we've done calculations, grams to moles, moles to grams, tell me if you all agree, we have done only grams to moles or moles to grams for the same compound. Okay, so we were able to take magnesium or water or whatever the example was and convert from grams to moles. Okay? Today, what's different is you're going to see this, is we're going to use a balanced equation. Okay, that balanced equation, we have a relationship between our compounds. And they're different, right? If we take methane and oxygen, we form water and CO2. Okay? And they have a mole-to-mole relationship. Okay? And so if you look out in front, that coefficient that we adjusted and changed to be balanced equations, we're going to be using those numbers, okay, in our sequence. Okay? You'll hear me say this a lot too. Grams to moles to grams. That's the sequence. Okay, but we're going to go into more specific details of what that means. But the main thing is we're going to take, so this is what's neat about it. So if you knew in the lab how many grams of methane, so let's use our methane equation. You knew how many grams of methane you started with. Okay? You can calculate how many grams of CO2 that you should form. Okay? Those are two totally different compounds, agreed? One's a reactant and one's a product. Well, you can calculate how much you should form, which this is something a chemist does. So before they start any reaction, they do this equation or they do this calculation to find out. Even in industry, even at they're making millions of pounds and trillions of pounds of chemicals, they're going to sit down and look at what they start with and how much they should produce, because they know they have to produce so much in a day, in a year, however much it is. Okay, in our lab, you've already done this. I told you to bring your lab. I don't know if you remembered that or not. I don't think I mentioned it again on the announcement. But you did this. You formed salt. Everybody remember doing that? Okay, that was your product. Okay, and so you didn't know how to do this, or you may have if you've had chemistry before, but you didn't necessarily know how to do the calculation to find out how much salt was I supposed to form? Okay, what was we call it a theoretical yield because it's theoretically how much should I make? Okay, and so today you should be able to go back and do your lab. Okay, so on Monday you'll need to turn in the lab from the last lab. That makes sense, but the last lab, y'all know what I'm talking about, the salt lab. Okay, you need to turn it in on Monday because you should be able to do it now. Okay. So I did some explaining, okay, but the first thing we're going to do is we're going to jump in because the best way to learn this is to start by practicing and looking at a problem, and we're going to go through the sequence together. I'm going to show you what I'm talking about with respect to the sequence, grams to moles to grams, okay? The first thing you're going to do is read the problem. So you want to know how many moles of CO, not just moles. You've got to look at what compound are you looking for. Okay, so if we look over here, it looks like here's our CO, right? Okay. So we want to find out how many moles of CO are required to react with 3.5 grams of iron 3 oxide. Okay. Does anybody have any idea why this would be useful if you were setting up a reaction in lab? Why you'd want to do this? So if you knew you had 3.5 grams of iron 3 oxide, aren't you going to have to calculate how much CO you're going to need in order to form the products? Okay, if you don't do that calculation, then it's hit or miss, and you might get a 30% yield, or the reaction's not going to go to completion or near completion if you don't do the calculation first to see how much of both reactants do you need, okay, to form the product. Okay, so we've got our reaction. Check it. Is it balanced? Make sure it's a balanced equation. Okay, that's why we learned to do that first. Okay, it looks balanced to me. Look balanced to you? Okay. First thing we're going to do is write out what we know here. Okay, here's our sequence. Okay, this is what we're doing. So each of those arrows, you can think of it as that's where you'd put your multiplication sign there. Okay. Okay. Depending on what you're asked for, you may not have to do all of these steps. So here's one step. Here's 2 steps. Here's 3. Okay. You're going to start with grams of what you know or you're known. Okay, so what's the compound here that's our known? The 3.5 grams of what? The iron 3 oxide, right? So that's our known. Okay, you're going to convert grams of what you know, the iron 3 oxide, to moles of your known. Okay, is that step going to be any different than what we've already learned? Exactly. The first step is just like what you learned in Chapter 2. So we're going to go to moles of our known. Okay, so we set this up. We know that we have to have grams here. Okay. To convert from grams to moles, we are going to divide by the formula weight, or the molar mass, of iron 3 oxide. Okay, so if we add that up, if you take 2 iron atoms plus 3 oxygen atoms, so oxygen 16 times 3. Okay, so we're using our periodic table here. Everybody get about 159.7 around there? Okay. If you use your periodic table, how many moles is this number out of going to be based on? 1, always. Okay, this is where this starts getting really important. Nothing changes. To this point, until here in a few seconds, we have only used 1 mole, right? Okay, so if you add up your formula weight, molar mass, on the periodic table, it doesn't matter how big the compound is or how small it is. It's always based on 1 mole, okay, because that's what your periodic table is based on. Okay, so we form 1 mole of iron 3 oxide. Okay, units cancel. All right, so what have we found at this point? Moles of iron 3 oxide. Okay, so can we stop here? Is that what the question asked? No. Okay, we're going to have to do one more step. Okay, we're going to have to convert from moles of what we know, that's what we just found, to moles of what we're trying to find. Okay. We don't have to do the last step because we're not asked for it. Okay, we could be asked for grams, and we're going to do that here in a minute. Okay, but we're asked for moles of what we're trying to find, and what's the compound we're trying to find? CO. Okay, so with any conversion factor, just like inches and feet, grams and moles, we have to have a common relationship, right? So in order for us to get from moles of what we know to moles of what we're trying to find, we have to use something that has a relationship between the two. Okay, what do you think we're going to use? This, our balanced equation. The whole point of balancing it is to show our relationship, our ratios. Okay, if we look here, we have 1 mole of iron 3 oxide for every 3 moles of CO. That's their mole-to-mole relationship. Okay, that's why we learned to balance an equation first, and now we're going to use it. Okay, this is the only step that you can have more than 1 mole, okay, in your calculation process. Okay, so to keep everything set up, we know if we have moles of iron 3 oxide on top here, we have to have what units down here? Moles. Okay, that way you don't get things flip-flopped. Okay, so you have to have moles, but not just moles. You have to have moles of what? Iron 3 oxide. That's why it's important to write out the name of the compound, to write the formula. Okay, you can't put moles of CO down here, then you're going to have it backwards. Okay, so you're going to put moles of iron 3 oxide, which in this case, it just so happens to be 1. Okay, it doesn't have to be 1. It just is in this problem. So we have 1 mole whatever that number is. Okay, we're looking for moles of CO. So this is where we plug in our relationship based on the coefficients. It's not a subscript. You look at the coefficient, the number out front. Okay, you have 1 mole for every how many of what you're trying to find, which is CO? You have 3, right? So we would put 3 moles CO. Okay. Bless you. Bless you. Okay, now do our units match up with what we're looking for? Yeah, we're trying to find moles of CO. Okay, so you can do this a number of ways. Some people have calculators. They just put it all in together. Or you can take 3.5 times 3 and then divide it by 159.7. Okay, and when you do this, your answer is about 0.066. Okay, and what are my units here? Moles, and not just moles, moles what? Of CO, of carbon monoxide. Okay, So here's our sequence. There's really just 3 steps. Okay? You have to look at the problem to see where you start in that sequence and where you end. It just depends on what the problem asks you to do. Okay? I may not ask you every time to go to moles. I may ask you to go all the way to grams. Okay? Just depends on the problem. Okay. Remember, mass is always in grams. And some people, I don't know why, but moles and grams are not the same thing, right? We know how to convert the two. Okay, this time we're asked for grams of CO. Okay. That's required to react with 146 grams of iron 3 oxide. Okay, so if we look at our sequence, grams to moles to moles to grams. Oops. Okay, before I move on, real quick, I'm using iron 3 oxide again as our known, and we're trying to find CO. Okay, you're going to see through practice in these problems that this relationship, this mole-to-mole relationship, can be for anything in the equation. Okay, so this is just the one that I'm specifically asking for in this problem. But if we wanted to, we could find grams of iron that we're going to form. Okay, anything in that balanced equation is fair game to be able to convert from one to the other. Okay? All right, so we start with what we know. We have 146 grams. That's what I'm always going to do first, and go ahead and write out this. All right. Next, I'm going to really pay attention to the problem, okay, and decide how many steps am I going to have to take in this problem. Okay, I know I always star this step because that's the step where you can have more than one mole there. That's our new step. We haven't done that besides just now today. Okay. We know we're starting with grams of a known, right? So we know we've got to start right here. That's where we're going to start. Okay. And if we're asked for grams of CO, which is what we're trying to find, how many steps are we going to have to take? We have to take 3, right? Okay, the last one we were asked for moles, so we could stop here. But now we're asked for grams, right? So we got to do all 3 steps. So this is where we're going to end here. Okay, I'd use the same equation, balanced equation, so we don't have to keep adding up the molar mass. So we already came up with our molar mass for iron 3 oxide. So it was 159.7, I think. Yep. Okay. And if we add up our molar mass, it's always grams per how many moles? 1. Okay. So this first step, there's really only one new step in this problem, and that's going to be our mole-to-mole ratio. The first step is just converting grams to moles, right? Just dividing by grams. Okay, and then you're going to see the last step is just converting moles to grams, just like we did in Chapter 2. Okay, so the only new step, really, is this middle step there. Okay, so we did our first step, grams to moles of our known. Our units cancel. All right, now we are to the mole-to-mole ratio step. This is our new step. When we get to this step, we have to use the balanced equation to get our mole-to-mole ratio. All right, so we know our moles of iron 3 oxide has to go on the bottom so that our units cancel. And we know that we have 1. We are once again trying to find CO, and we have 3. So if you look up here, we've got 3 moles CO. Okay? So very similar to the last problem, and this is where we would have stopped, right? We would have stopped at the moles. Okay? But we know that we've got to go one more step. So we did this step, and now we have to convert moles of CO to grams. Okay? When you convert moles to grams, you just multiply times, basically is what happens. You multiply times the molar mass of the CO. Okay, so we know that moles, or mole of CO, has to be here. Okay. So in this step here, we're now going to plug in for every 1 mole. Okay, remember, this step here is the only step that we can have more than one. Okay, we're going to plug in our 1 mole. And then how many grams do we have? Grams per mole of CO. How are we going to find that? The molar mass, exactly. So you're going to look at your periodic table. If it's out of 1 mole, you're going to have to use your periodic table to figure it out. So you've got 12 and 16, so about 28.01 grams. Okay. So this first step, grams to moles, is just like chapter 2. Okay, dividing by the molar mass. And the last step is just like chapter 2, converting moles to grams, where you multiply. The only difference here is we went from moles of iron 3 oxide, or grams of it, really, to grams of a totally different compound because we used a mole-to-mole ratio from a balanced equation. You have to have a balanced equation for these. Okay? If it's not balanced, you're not going to get the right answer, and you wouldn't be able to do the problem. Okay, questions? Okay, we're going to use the same equation. You'll see other ones in practice. Okay. So I want you to read this and think about where you would start. Okay, and then we'll kind of walk through it together. Okay, think about where you would start, how many steps you would have. If you want to write out your sequence, you can. This whole excess part, that just means that we have plenty of carbon monoxide. We'll learn more about what that means really today or a little bit later. Okay, but it means you have plenty of it, so you've got excess of it to react with the iron 3 oxide. Okay. Sometimes this is the hardest part of knowing where to start or knowing what part of the sequence that you're at. Okay, if you're given the moles of iron 3 oxide, okay, where are we going to start on our sequence here? At moles, right? You don't have to go, students will try to convert back to grams and then go back to moles and add all this extra work. Okay, if you're given moles, just think of it as you were given that first step. Okay, so where we're going to be starting is going to be here. Okay. Okay, we're asked for mass of carbon dioxide, so mass of a different compound that's related in our balanced equation. So we're going to go from moles of what we know to grams of what we're trying to find, which is carbon dioxide. Okay, so we write out what we know first. So what's our first step? Our first step is looking at our balanced equation, right? And coming up with our mole to mole ratio. Okay, so we bypass that grams to moles. We're already at moles. Okay, and now we already know we have 1 mole. Okay, and how many moles of carbon dioxide do we have? 3. Yeah, so we had 3 over here, but here's our dioxide. So we've got 3 moles. Okay, moles cancel. All we need to do now is convert from moles to grams. So when we do that, we end up multiplying times the molar mass. Okay, so if you add up CO2, I think it's 44.01, so 1 carbon and 2 oxygens. We used our periodic table, so that means it's always out of 1 mole. Okay, so you have to multiply everything there, 0.5 times 3 times 44, about 71.3 grams. Okay. So this is useful. So if you had that many moles, or if you were given grams, it wouldn't matter, of iron 3 oxide, and you had excess of the carbon monoxide, this is how much CO2 you would produce. A lot of times your industries as well will have to do these calculations based on the product that they want. They want to see how much product that they're going to form. But they also have to be careful. CO2 is not a pollutant, which is obvious, but there's oftentimes that pollutants are formed, so they have to do these calculations, try to figure out how much they're going to be emitting from their chemical reactions or from the industry. So very useful, to say the least. Okay, another practice. Like I said, we're going to keep practicing. So I want you to try to do this one on your own and see where you might have a problem, or maybe you don't. Okay, but read the problem first, decide where to start, how many steps you're going to have, and then go from there. I think we've pretty much added up all of the molar masses, so you shouldn't have to spend your time there. And raise your hand if you have a question. I'll come to you. Everybody about got it? Think? Okay, how many steps are we going to have to do here? We looked at our sequence. Okay, it's 3, right? So there's only 3 that we've done so far. Okay, so we have to go from grams to moles, moles to moles, and then moles to grams. Okay, so our first step is just dividing by the molar mass of CO2, which we already came up with, which is about 44.01. And that's always out of 1 mole. Okay, this is our mole to mole ratio. All that means is everything here has a ratio. If we looked at iron 3 oxide and CO, they have a 1 to 3. Iron, or just iron, Fe, and CO2, they have a 2 to 3, or we could keep going. So everything has a ratio based on the coefficient. Okay, so our CO2 has 3 moles. And then what are we looking for? What are we trying to find? What compound? The iron 3 oxide, right? Okay, and so we've already seen lots of times we have 1 mole of iron 3 oxide. So now we've done 2 steps. Okay, this being our new step where we use our mole to mole ratio. And now the last step is to multiply times the molar mass to give us the grams of iron 3 oxide. Okay. So when you do the math here, multiply everything on the top, everything on the bottom, divide, and get about 10.5 grams. So if 8.65 grams of carbon dioxide was produced, that means that the chemist started with 10.5 grams of iron 3 oxide. How many of you got that one? Awesome. Okay, have you try one more. This one is, I'll give you a hint, the simplest, but often missed on the exam. Okay, because students will try to do too much. So don't try to do too much on this one here. Everybody agree with how I started this? Okay. All right, how many steps do we need? exactly. Anybody try to do more than one step? Okay. Very good then. Y'all are picking this up fast. Okay. So if we're given moles and then asked for moles of a different compound, all we do is our mole-to-mole ratio. So we know we have 1 mole iron 3 oxide, and then we're asked for moles of CO. So 3.5 times 3 is about 10.5, which we would round because we only have 2 significant digits here. So it'd be about 11 moles. All right, any questions on those? Okay. We're going to do more practice here in a few minutes. So we've looked at grams to moles to grams. Okay, one thing that we haven't looked at or thought or brought into this process is Avogadro's number. Okay, so Avogadro's number was always 1 mole equals 6.022 times 10 to the 23rd particles, atoms, things, if you want to think of it that way. Okay, or it could be ions, molecules. Okay, so we can now put this in the mix. Okay. So same reaction equation, but this time we're given molecules. Okay, so this number, molecules, can we relate it? What's our relationship to anything? It's molecules per what? Per 1 mole, exactly. Okay, we can't directly relate molecules and grams, right? Okay, we have to go through moles first, which we did that in chapter 2. Okay, and so you're going to have to go from molecules to moles. Okay. Okay, I would suggest writing out molecules unless you can just, some students will abbreviate molecules for moles, and they're not the same. Okay, so don't do that. Okay? We know there are 6.022 times 10 to the 23rd molecules of any molecule, but this is specifically iron 3 oxide, in 1 mole. So in this example, so we've been looking at grams to moles to grams. So the only difference was that we had molecules to moles. Okay, and we used Avogadro's number, abbreviated Na there. Okay? We still have to go from iron 3 oxide to just iron. So here's our iron. Okay, so the only way that we can get from one compound dimensions to another is by using our what? Our mole-to-mole ratio of our balanced equation. Okay, so we have to do that still. Okay, so we have 1 mole iron 3 oxide, and we're looking for iron atoms. Okay, so how many iron atoms do we have? How many moles? 2. Okay. So if you were just asked for moles, then we would stop here. Okay. But we're asked for the atoms. So when we hear the term atoms, molecules, or particles, we know we have to use Avogadro's number, right? So we're going to have to use it again, okay? And so we're going to go and we're going to say in 1 mole of Fe, or iron, we have 6.022 times 10 to the 23rd. I'm going to abbreviate it as Na. That's shorthand for that number, for Avogadro's number. So we went from moles to molecules. Okay. Like I said, there's variations. We don't do these as much as we do our grams to moles to grams. The only difference here is that we weren't given grams, we were given molecules. So we used Avogadro's number in the beginning, and then in the end we were asked for atoms. Okay. And so we had to use it again. Okay. If we had been asked for grams of iron, what would have changed here? Yeah, so at the end, you would have just done 1 mole and then the grams of iron. And then that would have been your answer. Okay, so you just want your units. So I'll make sure my units match up here. So that was, okay, so the answer here, about 5.00 times 10 fifth. That's a 5 there to the 5th. Okay. All right, first off, let me go back a second. If we look at this, just to be sure everybody remembers this. Okay, on the left, these are our reactants, okay? And on the right, we have products. So most chemists' goal is to form products, right? In the highest yield. So and hopefully they form their desired products. So not a bunch of side products and things that aren't desired, okay? What do you think would happen if we were limited by iron 3 oxide? So we had excess of our carbon monoxide. Okay, so we have lots and lots of it. But what about if we run out? So these reactants are colliding, bumping into each other, breaking bonds, forming new bonds. Okay, what do you think is going to happen if we run out of iron 3 oxide? Is the reaction going to be able to keep going? No, it's going to stop. Okay, so if you are limited by one of these, that's going to be what we call your limiting reactant. Okay, so if you use it up and it's gone, meaning it's been completely converted to products or side products or whatever, okay, then the reaction stops. It can't go anymore. You don't have any more of one of your reactants. Okay, so this is the limiting reactant concept. Okay, so if you had 6 slices of turkey or ham or whatever you like to eat on your sandwich, and you had 10 pieces of bread, how many sandwiches could you make? Somebody said 6. Okay. Somebody said 5. Okay. Okay, so think about it. A sandwich has 2 pieces of bread. Okay, so 5. If you have a sandwich with 2 pieces of bread, you have more bread, right? But you need 2 for every 1 piece of turkey, okay? So you're limited here by the bread. You're going to run out, and you're going to be left over with 1 slice of turkey, okay? So if we think about this in chemical terms, the bread was your limiting reactant. Even though you had more, right, you needed more for the reaction or for the sandwich to be made. Okay, another concept here. Okay, look at this. What are you going to run out of? How many sets can you make here? Everybody agree with that? Okay, that's true. If we only need 1 bolt, then we can make potentially 87 sets. Okay, we need 2 washers. we have 110. We have the most that we have here is 110. So we have a lot of washers, but we need 2, okay, to make a set. Okay, so that means we're going to be left with just 55 sets. Okay, so that's what we're limited by. So if you were putting these together, okay, I want you to try to think of it in kind of real life terms. It's the same with chemicals. You can put them together and make new bonds or make sets only as much as you have. So if you run out of one and you need, 2 for every one of your other reactant, then it stops. You can't make any more sets. You can't make any more products unless you have more. Okay? Okay. So what we do, we have a new equation here. Okay. And we look at both reactants. Okay, so what's our reactants here? Just to be sure everybody knows. What are our 2 reactants? Okay. Okay, y'all know how to name. How do you name that? CS2. Okay. It's 2 nonmetals, right? So we use the Greek prefixes. Very good. So I think I heard Cassidy tell us, what did you say? Okay, almost carbon disulfide. Exactly. Okay, so we have carbon disulfide, and then we have oxygen. So those are our 2 reactants. And what we want to know is which one's our limiting reactant. Okay, whichever one is our limiting reactant, that's the one that we can use to find out how much product we can make. We can't make more than we have, right? Okay, we can't make mass or matter. That defies our law of conservation of mass. Okay. So what you're going to do is this time you're given 2 masses here, okay, for your reactant. Okay? You're going to take each of them. You're going to take the 95.6 grams of carbon disulfide, and you're going to convert to grams of sulfur dioxide. Okay? So you're going to go from 95.6 grams to moles to grams of the product. And then you do the same thing with the 110. So now you start with the 110 and go from grams to moles to grams. And then we're going to compare the 2. Okay? So take a minute just to kind of start it. And then I have this one actually already written up here. We're going to look at it. Okay, so take each one and convert to grams of sulfur dioxide. Okay, if you're thinking of your sets or your washers and whatnots and our sandwiches, if we think about it here, which one do we need more of to make a set, to make a product? Yeah, so for every 3 or for every 1 CS2, carbon disulfide, we need 3 moles of oxygen. Okay, so that's the big difference here. So we need triple the amount of oxygen, really, okay, based on molecular weight as well, though. Okay, so just take a couple minutes and convert each of these from grams to moles to grams. Okay, and then I'll put them up here and we'll talk about them. got them up here, so see if you're getting the same answer and understand why. So. Okay, we start with 95.6. Okay, you could start with either one, but that was the first one listed. First thing we have to do is find the molar mass. So add up our carbon and our 2 sulfurs. You should get about 76.2. And we know if we use our periodic table, it's always out of 1 mole. So there's our first step, grams to moles. Okay, and then our grams cancel. And we know to get from one compound to another, the only way we can relate the two is by looking at our balanced equation. So we have 1 mole of CS2 for every 2 moles of sulfur dioxide. Okay. And then the last step, we can take our 1 mole SO2, it's going to be on the bottom, so these cancel, and then we add up the molar mass of sulfur dioxide, which is about 64.1. So we get 161 grams of SO2. Okay, remember, this is our reactant. Okay? And this is how much product we could produce. All right? If we do the same thing for oxygen, notice that we have more oxygen, don't we? But why do you think this one ended up being limiting? Right, because you needed 3 times the amount. Okay, it doesn't mean oxygen will always be. It depends on the problem and the numbers that I give you. But when you go through this, so you have O2, so you divide by 32. You have a 2 to 3 ratio, whereas you had a 2 to 1 before. So if you divide by 3 instead of 1, you're going to get a smaller number. Okay, so if we then convert from moles, so here's our ratio, and then we use our molar mass of SO2, and we get 147 grams. Okay, you can only produce 147 grams of SO2. So it says, what's the maximum mass of sulfur dioxide that can be produced? Okay, so why do you think that is? Why is it the mass? Why is it 161? How much we would form? Do what? Exactly. So you run out of oxygen here. So here's our 2 numbers, but we know that oxygen we only have enough to form 147. So we can't get to 161 because we don't have any more oxygen. We ran out. So I'll probably ask you 2 questions with this, one on the exam or on whatever homeworks. You're going to have to tell me what's the maximum amount that you could form of a product, okay, which would be that answer there. Okay, but what's your limiting reactant? Oxygen. One of the most common mistakes is to tell me that this is your limiting reactant. Okay, the SO2 is not a reactant, is it? It's your product. Okay, so the limiting reactant is oxygen. Okay, so our limiting reactant is oxygen. Okay, questions? Okay, what we just did with our limiting reactant, and for your labs, everybody listen up, lots of talking going on here. Okay, going from grams to moles to grams, that's what you need to do on that lab from the previous week, from last week. What you're finding is what we call the theoretical yield. Okay, that's what we just found. Okay, so this number right here, that's theoretically how much product we should make. So what you find is you're going to use your balanced equation, Okay, and you're going to find of your baking soda or sodium carbonate and HCl were your two reactants. Okay, everything's a 1-to-1 ratio, so it's pretty easy. Okay, you formed CO2. You remember you had the bubbles that came up, and salt. And so you take your grams, how much ever baking soda you used, and you convert to moles of it. Then you use your balanced equation to go to moles of salt, and then you use your molecular weight of salt, okay, to go to grams of the salt. Okay, and so you are finding this whole process that we're doing on paper is the theoretical yield, meaning how much theoretically we should make. Okay, but in reality, when you're in the lab, are you going to make 100%? No. Okay, there are really essentially no reaction that you will make. There's 99.9, but there's never a reaction that is 100% efficient. Okay, there's always a minor room for any kind of error that could go on. Okay, so this number that you calculate is just your theoretical. That's how much I should make. Okay, but when you're in the lab, we come up with an actual yield. Okay, your actual yield, that's how much you actually got in the lab, in your beaker or in your Erlenmeyer flask. Okay, so on your lab, you should have, I formed 1.1 gram, 0 grams of salt. Okay, what you actually see and saw in the lab is your actual. Okay, so if you take your actual yield, that's what you obtained in the lab, and you divide it by your theoretical, which is what we just learned to calculate, times 100, that gives you a % yield. Okay, most every reaction that chemists do, this is what they report. Okay, so they do their calculation to find out how many grams of each reactant to use, and they find out what their theoretical yield should be. Then they run the reaction, and they actually get a yield in the lab, and they find their % yield. Okay, so what do you think? So % yield, can it be over 100? No. If you get over 100, so I'm giving you another answer to your lab. Okay, if you get over 100, what do you think could have happened? Okay, you could have miscalculated. Yeah, you didn't write your. There's a lot of things, so you didn't write your numbers down. You may have used too much. Okay, but when you had to put your flask under the hood and you had to heat it and draw off all the water and all of the HCl, what could have happened is that you didn't let it heat long enough. So you have water or you have something else on your salt, and that would give you a higher yield. Okay, but it'd be impure, right? Because it's not salt. It would be the water or whatever that didn't drive off. Okay, so this is what you'll do at the end of this lab as well as the aspirin lab. So come Monday, you'll be, hopefully, if you study this and understand it, you'll be right along pace to convert grams to moles, moles to grams, find your theoretical, and then find your % yield. And so the higher the better. I mean, that's what industry, that's what they do. They work on methodologies and different ways that they can produce, very high percentages. Okay? Because the more money you waste if you don't produce high % yield. Yes? Mm-hmm. Of what? Of just any chemicals that we have in the lab? None of them are going to say 99, or none of them are going to say 100%. The most you're ever going to see is 99.999, which is basically saying, we just can't, there's that very slim margin for error, so nothing is 100%. Most of our ionic compounds are going to be in the 99% range. So when we have calcium bromide, sodium, of course, sodium chloride, anything like that, your ionic compounds tend to be more pure. Yeah. But I don't know exactly what % would be 99%. Maybe 50% of the chemicals we have would be about 99.99. Okay, still have a few minutes. We didn't get to the worksheet, so that's where we'll start. So please bring these. They're labeled in-class problems for Chapter 3. You can go ahead and be working on them as well. But before you leave, I want you to try this problem, show it to me, and show me what your answer is. Okay, and then you can, when you show it to me and you got it correct, then you're welcome to leave and have a good weekend. All right, and bring this on Monday. All right, this one's simpler here because we've got everything's a 1-to-1. So still show that ratio, 1-to-1, okay, but it's not really going to change a whole lot. So a couple hints here. You've got 10 grams of ethanol and excess acetic acid. So I already told you that this is your limiting reactant, right? Okay, because you have excess of acetic acid. Okay, so here's acetic acid. Here's ethanol. Okay, and this 14.8, that is your actual. I'll give you one more thing. Your molar mass, this, since we're kind of cutting it close, is 88.12 grams. And this is ethyl acetate. Okay, so go from grams to moles to grams. Okay, your product's the ethyl acetate, so that's what you're looking for. And then once you find your theoretical, then find your percent yield by taking actual over theoretical times 100. And once you've got it, just let me see it as you go out so I can know who may have problems with this and who doesn't. 14.1. Very good. Thank you. Okay. I don't know. It is that, isn't it? You got a really high crest, I think, and then you have a miss. Okay. Thank you. You're welcome. Okay. Looks good. Go ahead and show me what you got. So you got 19. Yeah. So I got 19.1. So you got 19.2. That's right. Very good. You just have one less sig fig there, just being, but it looks good. Yep. And you just, if you think about sig figs, you just have 3. Yeah, because you have 10.0, so be sure you keep all your numbers there. You got 3 in the beginning, so you need 3 at the end. Mm-hmm. Good. Same here. You'll need just 3 sig figs because you got 3 there. Looks good. Okay, same with you. 3 sig figs because you just got 3 in the beginning. But, yeah, looks good. And then you need your percent yield. Yeah, so take your actual, that 14.8, you don't have to show it to me again, and over 19.1 times 100. Yep, and that would just be 3 sig figs there when you report it. But good job. Got it? Okay. Okay, all you did was get these backwards. Yeah, so you would put that on top, and you would get about 77. So just switch them. Anybody else? Looks good. Thank you. Good job. Okay. Okay. Very good. Yep. And you just put percent, of your product there. Theoretical. Yeah, the theoretical is the one you calculate. So the one that you went grams to moles to grams, that's the theoretical. And the actual is 14.8. Yep. I'm just going to catch you real quick before you. Okay, so where you messed up. Okay, so be sure you've got a 1-to-1 ratio there. That's right, but that is 46.08. So you just added it up wrong or something. So that should be 19.1. 19.1 grams. Okay. Thank you. Yeah, you're fine. Thank you. All right, another couple minutes. I think they're waiting on us. Okay. Yeah, you don't have to do that. Yeah, because you end up just canceling everything. Yeah. So just find that. There you go. Yeah, and then just keep 3 sig figs here because you got 3 in the beginning. So 10.0. So that'd be 10.0 right there. Ready? Okay. Good job. Okay. What'd you start with? What number did you start with? Okay. Okay. Doing way too much work.
Okay, on this
Yep.
one or both of them?
Yep.
Okay.
This right here, you did 10, 46.08, 1-to-1, and then All right.
Do we go to the CH?
No, because you're told that you have excess. So excess means you have, yes. So you're only using the ethanol. So what you needed to put here was y'all went to ethyl acetate, I think. Or you went to acetic acid. Ethyl acetate is your product, right?
Yeah.
Ethyl acetate. So it is 88.12 grams per mole. So it needs to be there is 88.12. Okay, you don't have to do both like we did in the other because I told you which one was the limiting.
And then...
Because see, you don't know how much acetic acid you have. Okay, so get your answer there. That 14.8, that's your actual. Okay, yeah, you did extra work there too. You don't need to do. Okay, thank you. Okay, I think what happened here. Okay, when you add it up, see that's ethyl acetate. That should be 88. See, 88.12 up there. And that's going to give you 19.1. So see, it can't be over 100. So that would be 19.1, and that's going to give you 77.5. Good deal, yeah, and just keep 3 sig figs there, since you got 3 to start. Okay, so you did, this is right here. Okay, but that right here should be 66, should be the 88.12 that I have up there. So you get 19.1. And then all you do is take 14.8, divide it by 19.1, see that goes right there, times 100. And that gives you your percent yield. Okay. Thank you. All right, go ahead and show me what you've got. We're holding up the next class. You got 19.1, and then what's your percent yield? Okay? Percent is actual over theoretical. That 14.8, that's your actual yield. See? So you take 14.8 over the 19.1 times 100. Okay?
I got a scholarship, and I have to fill one of these out. Could you?
Okay. Let me see. Yeah. This is Chem 111. You're not in 112, are you?
No.
Okay. Do you know what this is?
I think it's B right now.
Okay. I'll just go. And have you missed answers?
Hey, Ms. Hendricks, I have the same exact things he does.
Okay.
Thank you.
Let's do them real quick. You're welcome. All right. Do you know what it is? Okay. Have you missed? There you go. Yep. Yep, that's fine. Yep, did y'all understand how to do it? Okay. All right. Because you're given excess, that means you don't have to find a limiting. I tell you what it is. Okay? Thank you. Yep. See ya. All right. Sorry, we're running over. You can come on in. I'll get out of the way. All right. Go ahead and show it to me if you've got it.